Welcome to another episode. This time we leave the traditional blacksmithing and enter the realm of high-tech. In this video, I will show you how to 3D scan an old artifact like this axe head. This technique is called photogrammetry and is also used by museums to scan and better understand their artifacts. The basic idea is to take many photos of an object from all kinds of angles and then use fancy computer software to digitally reconstruct it. I made myself a little turntable and painted everything green to better separate the object that is being scanned from the background. For turntable operations, the background needs to be completely masked away, or otherwise the software gets confused and cannot do the 3D reconstruction. Before explaining the principles behind photogrammetry, let me talk a little bit about the process. The camera is using a 50mm fixed lens and all settings are completely manual. The aperture is set to f/22 and the focus is set manually. The trick with the lighting is that it needs to be at the same position and angle as the camera lens. No matter which angle we photograph, the lighting should be identical. This axe head is a few hundred years old and heavily rusted from being exposed to the elements. That means there are no reflective surfaces, which is ideal for this. This process would not work with a shiny metal object. To scan reflective objects, they may need to be prepared with powder or removable paint. Another complication for the axe is that we want to scan the eye as well. For that, I am rotating the camera to multiple heights so that we can see inside the eye. You will see in a moment that this is not a traditional video for me, since I'm actually showing you screen captures from the software that I use to create the 3D files. Many of you may find this not very interesting, but I hope at least it will give you an idea of what is involved, especially now that everything 3D is becoming much more popular. So, let me take out the compact flash and then we can go down the rabbit hole. Since I'm shooting in Canon RAW, I need to first convert the files back to JPEG and also save them as a numbered sequence of files. One thing I'm noticing here is that the set of files was not exposed properly. This happened when I forgot to raise my continuous lights after raising the camera. It's okay, because I noticed while filming and retook that set of photographs. However, I don't want to use those photos for the photogrammetry process. What I'm showing now is the procedure for masking out the green screen so that only the axe head remains, as well as manual adjustments to create a better mask. I will not explain what I'm doing here, but instead talk a little bit more about photogrammetry. I am no expert in this area, so be forewarned that this explanation may be somewhat inaccurate. Let's assume we have a rigid object, such as the axe. I took several different photos of the axe, and when looking at these photos, we can identify identical features, such as a speck of rust on multiple different photos where the axe head moved in relation to the camera. Let's assume we can find multiple such features, tens of different points, on multiple different photos. We can now look at how much these points each moved in different photos. We know that the camera parameters are fixed, and we also know that the different points are not moving on the axe. This information makes it possible to compute the exact camera position relative to the axe for each photo, as well as the 3D locations of the feature points. I'm using AGSoft Photoscan, and it automates this whole process. First, I need to load all the photos that I took, and then tell Photoscan that it should read the mask I created from each photo's alpha channel. I quickly verified that this is really true and then asked the software to find a lot of feature points common across several photos. The turntable makes this more tricky because the camera really did not move. However, by telling the software to find feature points only in the areas that have not been masked, we simulate that the camera moved and the axe remained still. The software now finds the virtual position of the camera for each photo and also computes the 3D feature points I had mentioned earlier. This creates a sparse point cloud that Photoscan calls type points. Here you can see all the camera positions and the initial point cloud that we can inspect to get an idea if the software is understanding the shape of the axe. So far it looks pretty good. The next step is to create a dense point cloud, which is millions of points in 3D space that accurately conform to the shape of the axe. This takes quite a while to compute. As we can see, the points are so dense that we cannot really tell them apart anymore. I'm quite pleased with the results, as everything seems to match perfectly, including the eye of the axe. This is really all we need. Now I will tell the software to compute a 3D mesh and the texture map for the axe. The texture is really just a continuous photo of all the surfaces and can be used in 3D programs to render the axe, as you saw in my little intro sequence to this video. The mesh looks really nice as well. You of course may wonder why anyone would go through all that trouble. In this video, I will 3D print a copy of the axe and also show that important detail in the eye has been retained as well, and may yield some clues about how the axe was made. As you may be able to tell, I'm quite fascinated that this process worked so well. While not all intricate details such as the tiny rust pits has been retained, with the current number of photos about 70, a lot of detail is available nonetheless. I was hoping that I would be able to print a full-scale copy of the axe and also use the 3D model for precise measurements. Reality is intervening. I'm measuring the whole axe at roughly 7 inches in length. Yes, that's about 178 millimeters in metric countries. Unfortunately, my 3D printer has a maximum print size of 6 inches. For demonstration purposes, I'm printing it anyway, just a little bit smaller in size. As with anything, things are never simple. Here, I'm finding that the 3D model is not oriented appropriately. Fortunately, the software, with some trials and tribulations, allows me to reposition the axe on the virtual print bed. This may be a good time to talk about the difficulties with 3D printing. I'm using a filament deposit method printer with a single printhead. That means that any areas that would hang in the air need to be supported by so-called supports that get printed as well. The supports need to be removed and cut away later. Another problem with 3D printing is adhesion to the print bed. I am using HIPS as a material which contracts as it gets colder and has a tendency to pull away from the print bed. I had to print the axe twice before I was able to get a successful print. Everything you are seeing here is shown several times faster than it happened in reality. This whole project took about a day. Just printing the axe head took about 3 hours. Alright, now it looks positioned correctly, so it's time to start up the printer. That said, before the software can print, it first needs to compute all individual layers, which takes quite a while as well. When looking at the layers though, we can get a good idea of how the printer is going to put the axe together. This also allows us to see the infill, which sort of looks like a honeycomb pattern. For the material I'm using, the printhead needs to be heated up to 235 degrees Celsius and the print bed needs to be at 110 degrees Celsius. This is all quite hot and touching is not recommended. I'm using a Loudsspot Mini 3D printer, which automatically levels the head relative to the print bed, which makes it much easier to use. Let's watch how the axe is slowly being printed. The video quality is not the greatest here since I did not set up any lights, and this was printing at night. I think it's still good enough to get the sense of the process though. As you may be able to see here, the print already separated from the table, but not before it was done. Lucky me. Otherwise, this would have been another failed print. Removing the supports takes quite a bit of time as well. I did not sand the model afterwards, but cleaned it up as good as I could. Here is the final result. Given all the challenges, this looks pretty close to the original. Let's take a look with a flashlight at details in the eye as well. Thanks for everyone's patience with my slow video production, and to those of you on Patreon. As an extra goodie, I will make the 3D file of the axe available as a benefit on Patreon. See you next time.